A graph G with at least 2 points is bipartite if and only if all its cycles are of even length. Proof. Part 1. Suppose G is bipartite. To prove G contains a cycle or of even length. Since G is bipartite, then V can be partitioned into two subsets V1 and V2 such that every edge joins a point of V1 to a point of V2. Now consider any cycle V0, V1, V2 and so on Vn is equals to V0 of length n. To prove n is E1. Suppose V0 belongs to V1, then V2, V4, V6 and so on belongs to V1, and V1, V3, V5 and so on belongs to V2. Vn is equals to V0 which belongs to V1, and hence n is E1. Part 2. Assume that G contains a cycle R of even length. To prove G is bipartite, that is, to prove every line of G joins a point of V1 to a point of V2 without loss of generality, we assume that G is connected. Let V1 is belongs to V. Let V1 is equals to V1 is equals to V belongs to capital V. D of V1, V is E1. V2 is equals to V belongs to capital V such that D of V1, V is odd. Clearly, V1 intersection V2 is equals to null and V1 union V2 is equals to V. To prove every line of G join a point of V1 to the point of V2. Let U, V is belongs to V1 or adjacent. Let P be a shortest V1 U path of length m and Q be a shortest V1 V path of length n. Since U V belongs to V, both m and n are even. Now let U be the last point common to P and Q. Then the V1 U1 path along the P and the V1 U1 path along Q are both shortest paths and hence have the same length, say I. Now the U1U path along P, the line UV followed by the VU path along Q from a cycle of length m minus I plus 1 plus n minus I is equals to m plus n minus 2I plus 1, which is or not. This is contradiction. Thus, now two points of V1 are adjacent. Similarly, no two points of V2 are adjacent. Therefore, every edge of G join a point of V be a point of V2. Therefore, G is bipartition.